In order to ensure that the block will make it around the loop, we need to do a force balance of the block at the top of the loop to see how the normal force and the gravitational force affect the block. Let's first draw all of our forces acting on the block. We know that there's going to be a normal force and a gravitational force. So take a second to think about which arrow out of arrows 1, 2, and 3 represent the normal force, and which arrow out of arrows 4, 5, and 6 represent the gravitational force. Feel free to pause the video if you need to think about the answer. Now that you've had a second to think, the normal force will be arrow 1 and the gravitational force is going to be arrow 6. If we think back to video 1, we know that the normal force is always perpendicular to the surface that the object is in contact with, and the gravitational force is always acting straight down. With our forces set, we need to do a force balance. Using Newton's second law, we know that our object will have a force equal to the mass times the acceleration. And we know that the summation of the two forces in this case are the normal force and the gravitational force. We're going to denote the normal force as n and the gravitational force as the mass of the block times the acceleration due to gravity. We know that the acceleration, or that a term, can be written as the velocity squared over r, where r is the radius of the loop. Plugging that in, we'll get that mass times the velocity squared over r equals n plus mg. When the block is at the top of the loop, we know that the object is on the verge of losing contact with the surface. So we're going to assume that the normal force in this case is 0. When we rearrange the equation, we can figure out that the velocity of the block at the top of the loop can be written as v equals the square root of gr, where again, g is the acceleration due to gravity and r is the radius of the loop. Now that we know the velocity of the block at the top of the loop, we need to do a force balance using the conservation of energy principle discussed in video 1 to determine what height we can drop the block from so that it will go around the loop. So first, let's start off with that equation. We know that the sum of the kinetic and potential energies at the initial state equals the sum of the kinetic and potential energies at the final state. For this problem, our initial state is going to be at the release point when we're releasing the block, and the final state is going to be when the block is at the top of the loop. For the initial kinetic energy, the equation is 1/2 mv squared, but since the block is at rest at the release point, that goes to 0. The potential energy at the initial point, or the release point, is mgh, where m is the mass of the block, g is the acceleration due to gravity, and h is the arbitrary height that we are going to solve for. The final kinetic energy is going to be 1/2 mv squared, and I've substituted in the v that we solved for previously, which is the square root of gr, and the potential energy at the top of the loop is going to be mg times 2r. And that 2r term comes from twice the radius of the loop, since that is the height when the block is at the top of the loop. As we go ahead and start solving our equations, given what we have, we'll determine that the height that we need to drop the block from in order for it to go around the loop is 5/2 times the radius of that loop. All right, now that we know what height we need to drop the block at, let's do a demo with it. But I'm going to substitute a ball in for a block. This track is a bit oddly shaped and a block isn't going to go down the ramp as easily, so I'm going to use a ball instead. All right, 3, 2, and 1. And as we saw, it made it through the ramp, and it made it through the ramp just perfectly fine.